Okay, I'll get used to this. All right, so I want to remind you of Newton's method and how far we had gotten last time. So if you'll recall, Newton's method has two phases, phase one and phase two. Phase one is what we call damped Newton's method. And so you can see here that there's this eta that's set less than one, and that's what's called phase one. And then phase two is undamped. And phase two is when we have our quadratic convergence. We had also talked about backtracking line search. This is an algorithm that is very generally used. If you'll recall, whenever you need, you want your step size to depend on certain parameters of the problem. That doesn't make sense if you don't know what those parameters are. And as we discussed last time, backtracking line search is a way for us to automatically find them. The theorem for Newton's method says the following. I want to spend just a moment emphasizing again what the assumptions are. So, this first part here, this is pretty much our standard assumptions that we would want. F is convex. In fact, it's strongly convex with parameter little m. It's smooth with parameter capital M. And then we have the new condition, which is that the Hessian is itself Lipschitz. So the Hessian changes slowly. Okay, so this is that condition. And remember, we talked about the operator norm last time. So this is the largest absolute value of eigenvalue. If the matrix were not symmetric, in this case, we're only interested in Hessian matrices, so these are always symmetric. But if they're not symmetric, then the operator norm is defined as the largest singular value. So the theorem says the following. There exists some constant, lambda, so that the key part is as follows. As soon as the gradient is small enough, then we have quadratic convergence. And this is pretty much where we stopped last time. And I was pointing out before we get to the proof, what is the consequence of this statement? And again, just to belabor the point here, linear convergence is when xt plus 1 minus x star is less than some constant less than 1 times xt minus x star. But that's not what's happening here. We have no guarantees about what L over M is. And the point is this square. That's the key. So let's see what's going to happen. So first of all, in the other part of the theorem, which we had discussed last time, is that phase one, you're guaranteed to make constant progress. And so we're only going to be in phase one for a limited number of steps. So let's move on to understand what this phase two promises. Okay, so this is so phase two says the following. If the gradient is small enough, we know by smoothness and strong convexity that means that xt is close enough. So instead, let's consider what happens if we have this condition. And again, the point is that this is not something we can evaluate directly. You can evaluate the gradient and evaluate its magnitude, but if you don't know x star, you don't know how far away you are from x star just by looking at xt. But because of strong convexity, we have this property. So and this was the very last thing that we did on Thursday before spring break. And just looking at the iteration, xt plus 1 is equal to xt minus the Hessian inverse times the gradient. And xt plus 1 minus x star is less than L over M times xt minus x star squared. This is the consequence of the theorem. So we're now I'm not proving the theorem, I'm saying why is it that this result is so great. So this is from the consequence of the theorem. And now I know something about xt minus x star by my assumption. So let's plug that in. Xt minus x star squared is m over 2l squared. And now I'm just shifting things around. So I have two m's up top because of the square. One of those is going to cancel this. I have two l's on the bottom. One of those will cancel that. So I'm left with m over 2l without the square. And my extra copy of 1/2 I wrote out here. And now we can repeat. So one thing that we notice is that if xt minus x star is less than m over 2l, and xt plus 1 minus x star is less than half of that, then xt plus 1 minus x star still satisfies this assumption up top. And so repeating this, we find that xt plus 2 minus x star is less than, we just repeat exactly this thing, plug in the recursion, and you'll find that it's less than 1/2 cubed times the same quantity m over 2l. And then if we repeat again, just carrying out the simple algebra, you'll see it's 1 over 2 to the 7th, etc. And what this looks like is exactly this final term. So after k steps, if at some point xt, you're close enough to x star, you're this close, after k additional steps, your distance to x star will be 1/2 raised to the 2 raised to the k. So whereas linear is 1/2 to the t, quadratic is 1/2 raised to the 2 raised to the t. So this is very, very straightforward. Where was I stuck last time? I was stuck because I was trying to translate the gradient condition that tells us that we're in phase 2 into this condition. So I'm going to leave that as an exercise for you to go back and see how do you use the assumptions in order to have a condition just on the gradient rather than having a condition on xt minus x star. Okay, so where are we so far? We've basically shown that if we have these certain assumptions, our assumptions are strong convexity, smoothness, and Lipschitzness of the Hessian, then in phase 2, which we're guaranteed to enter after a finite period, we have this quadratic convergence. So log 1 over epsilon. So now we're gonna give the proof of Newton's method, just of phase 2. So okay, let me just switch back to gallery view to see if everyone is with me. If you're not, speak up or something. Okay, so let's look at how phase 2 works. It's pretty close to what we've seen in terms of the tools. So again, we're assuming f is strongly convex. We're assuming it's Lipschitz, and its gradients are Lipschitz with parameter capital M, and its Hessian is Lipschitz with this parameter L. And we're also assuming that we're starting, I'm not calling it xt anymore, I'm calling it x0. We're assuming we are starting at this point that's close to the optimal solution. We're going to use our friend, the fundamental theorem of calculus, which says that the integral of the derivative is equal to the function evaluated at the 2 endpoints. We've used this trick many, many times. So how are we going to use this? The integral, I'm going to take the derivative of the gradient. And so the fundamental theorem of calculus tells me that this is the function evaluated at its 2 endpoints. This is an integral with respect to one single variable, even though f is a function of n variables. So it's a function of t. Evaluated at t equals 1, I get gradient of f of x plus d. That's what's over here. minus the integrand evaluated at 0, which is just the gradient of f of x. Now use the chain rule. The chain rule is going to bring out this additional factor of d here. And I'm going to apply this using x as the optimal solution, x star, and using d as the direction from where I currently am in my kth iteration to the solution x star. So I'm literally just plugging in what I had. So I've written it again here. I'm using x is equal to x star, and d is equal to xk minus x star. So I have the gradient of, let's just remember how did we go from how come there's not a d in here? So let me I'll try not to flip back and forth too much. But let's see what's happening here. I've got an x plus d. X is x star, d is xk minus x star. If I add those, I just have xk. So that's where this is. I have gradient of f of xk. This is an unconstrained problem, so at the optimal solution, the gradient is 0. So this goes away. And then this is just what I had on the right-hand side. So now I have an expression for the gradient of f at xk. And it's equal to this integral of the Hessian dot product with xk minus x star. So now let's look at xk plus 1 and put into play the undamped Newton step. Xk plus 1 is xk minus step size is equal to 1, so there's no eta here, times this is the Newton step. And note here what I'm going to do. I'm going to write x, so I subtract x star from both sides. That's what happened here. And then I rewrote xk plus 1, xk minus x star by multiplying by the identity. And I'm writing the identity as the inverse of the Hessian times the Hessian. And I'm only doing that so that I can bring it into the integral. So this is what happens from here to this step. Xk plus 1 minus x star becomes Hessian inverse times a Hessian times this. And so here it is, sitting out here, multiplied by the Hessian here, and multiplied by its inverse. So we haven't done anything different here. Now I'm going to use the submultiplicative property of any norm. The norm of AB is less than or equal to the norm of A times the norm of B. You can think about this as basically it's Cauchy-Schwarz. And I'm also going to use the fact that the absolute value of a sum is less than or equal to the sum of the absolute values. This also holds for the norm. So the norm of the integral is less than or equal to the integral of the norm. I take the norm of both sides of this. Xk plus 1 minus x star is less than the norm of the right-hand side, and now I'm going to use the submultiplicative property, and I get the norm of the Hessian inverse plus the norm of this, and this is exactly where I'm going to use. This is where I'm going to use my the Hessian property of the Lipschitz property of the Hessian times xk minus x star. So now let's look at this. Let's look at this a little bit more carefully. So now I can use the fact that this is L Lipschitz. And what is the difference of their integrands? I have xk here, and I have x star plus t times xk minus x star. So the difference here is, so I can rewrite this entire thing, the difference between xk and this, as 1 minus t times xk minus x star. And that's exactly what is over here. So I'm upper bounding this non-negative value by L times the absolute value of what was inside, the norm of what was inside, which is just 1 minus t, which is what's in this box, here. Okay, I have a few more quantities that I need to bound. So going to the next page. This is easy. Here we just perform the integral. It's just an integral of 1 minus t. That's the same as the integral of t. So that's t squared over 2 evaluated at 0 and 1 gives me 1/2. So this whole thing just becomes L over 2. Okay, so now let's look at what we have. Let's look at this quantity here. So this is the operator norm of the inverse Hessian. We said the operator norm is the largest eigenvalue when a matrix is symmetric and positive semi-definite. It's the absolute value. It's the largest absolute value eigenvalue, but since the matrix is positive semi-definite, all its eigenvalues are non-negative. So this is what I've written here. So it's this is saying that the operator norm is the largest eigenvalue, and then the operator norm of the inverse, we're of course assuming the inverse exists. That's saying that the matrix is positive definite, and we already know that to be true because we've assumed strong convexity. The operator norm is the largest eigenvalue of the inverse, which is exactly equal to 1 over the smallest eigenvalue. And we know the smallest eigenvalue is controlled by the strong convexity parameter. So the smallest eigenvalue is lower bounded by the strong convexity parameter, and therefore the largest eigenvalue of the inverse is then upper bounded by 1 over that quantity. So we put it together, and we have xk plus 1 minus x star on the left. The key thing to notice is that this square emerged. So we have this square term. So that was the key that happened. So let's see again, where did that come from? We already had one copy here. So you see we have no square. We have no square over here. But then by Lipschitzness, this brought another copy of xk minus x star. So that's where we got the star, and that's the result that we need. Okay, we went over this pretty quickly. That's what happens when notes are pre-written. So for the remainder, we're going to slow down to our usual pace, because I'm not gonna be writing out the notes. But I wanted to wrap up Newton's method. This is something that I'd hoped to finish before the break. Key parts, key summary here is again that we have this extremely fast convergence, this quadratic convergence, log 1 over epsilon, as long as we're close enough. Questions, thoughts here? Okay, so in that case, my plan at this point is to continue on to interior point methods. So here's what I'm going to try to do. I'm going to stop this video and then restart it. And my instruction to myself doesn't need to be on video, so let me.